All right, folks, I think I got started here. New iPad, and so I had to figure out how to screen record so I can post it, and none of the controls were in, so I had to like add them all one by one, but I'm good now. I have a microphone, and I think we can start. And I think this is, it looks like it's not working, but it actually is. I see something coming out of the projector, but I don't see anything here. Kind of, is that visible enough? You guys can see that okay? We'll go with it. Okay, so welcome everybody. Today we are going to be doing a tutorial based on anything you want to ask from units 1 to 4, which is what the midterm on Thursday is going to cover. I have nothing prepared. So what that means is I will be here to answer your questions, and when you guys are out of questions, we're done. The questions can be specific. You can say, on assignment 3, question 4, you know, and give me a question like that. I have my laptop here, so I have some ability to search for things, but if you have it like handy, you could bring it to me too. Or if you prefer, you could ask me something more general. Like, can you go over the different functional groups or something like that? Or what makes a ketone different from an aldehyde or anything along those lines? So with that, I'm going to open the floor. Yes?
Can you go over how to draw a constitutional isomer? And there's an example from the fall 2022 midterm one.
Okay. And
Question 2.
okay, so when it asks for the constitutional, does it give you a structure or does it give you a formula?
A formula.
And what's the formula?
C2H3BRO.
H3BRO.
Yeah.
Okay. So the way I would do, and there's no charges or anything?
No.
Okay. So this is the formula, C2H3BRO, and we're asked to draw one isomer or several?
All possible.
All possible isomers. Okay. So the way I would look at this is usually the carbons make a skeleton. So I see that there's 2 carbons here, so I would start with a carbon-carbon bond, just like that. And then when you see what else is attached, we have hydrogens that like to make 1 bond each, bromine that likes to make 1 bond each, and oxygen that likes to make 2 bonds. So there's lots of different ways we can draw this one, actually, I am guessing. One is for the oxygen, you could imagine putting a double bond on here. And the 3 hydrogens we can stick on the other carbon, like this. And you could also put the bromine over here. So that's a structure that fits the formula. And so you can see, if you want to draw all the lone pairs, you can put all the lone pairs in too. I don't know if it asks for that in the question or not. And then you start looking at what's attached to this molecule, and you could start thinking about rearranging some things. So one thing you could imagine maybe doing is switching the bromine with one of the hydrogens. So you could draw something like this. Like that. And I'm going to draw something else and ask you a question. What if I drew this? So in the top one, the bromine is going down, and in this one, the bromine is going to the left. Are these the same thing or different things?
Aren't they the same because it rotates?
Yeah, these are the same, because that's a single bond right here, and you can just rotate that bond around and make those two the same. So that's not a new one that I drew there, so I'm going to get rid of that one. I don't know how to get rid of that. Maybe the eraser button. That'll have to do. Okay, notice we made a carbon-oxygen double bond. We didn't have to. We could make a carbon-carbon double bond. Those are our only two choices, though, because you can't make a carbon-hydrogen double bond, and you can't make a carbon-bromine double bond. But we can make a carbon-carbon double bond that looks like this. And then we have, I guess, two hydrogens on this side. We could have an OH over here and a bromine. I'm surprised we would have asked for all possibilities, because there's lots of possibilities in this case. And then you could do the same thing, and you could switch the bromine onto the other side. Back. C, C, OH, H, HBr. You could draw C, C. I guess this one, that's a stereoisomer. I'm not going to talk about that. So I guess those are our possibilities. There's one more possibility. We could have a ring. So if you had a ring, you'd have an oxygen, a carbon, and a carbon. Hydrogen, 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 bromine. So I guess that's a possibility as well. And all of these are different structures that have just that same formula, which is 1, 2, 3, 4, 5 structures. I don't know how many are in the solutions. I typically, personally, I'm not a big fan of open-ended questions like that. Like if I was asking a question like this, I might say, draw 3 isomers that have this formula, or something like that. I like to just have limits on it, because with questions like this, sometimes you don't know when you're done, but that's where we're at in this particular case.
What's the difference between this, which was, I think the question was constitutional isomer, versus resonance?
So resonance are different. So with the constitutional isomer, what we are doing is we're moving atoms around. So we're swapping one atom for another atom and putting them in different places. With resonance structures, atoms themselves never move. The only thing that moves in resonance structures is electrons.
Okay.
And I can do an example if you like.
Yeah, sure.
So yeah, let's say I gave you an example that looks like something like that. And you're asked to draw a resonance structure of this thing. Does that look okay, by the way? You can see that fine? What I like to do when I get a question like this is draw in all the lone pairs, at least, to begin with. So the nitrogen needs 8 electrons, so it gets a lone pair. How many lone pairs does the oxygen have? 3 lone pairs. So it's got 1, 2, 3. And how do you know it's got 3? Well, it needs 8, first of all, to have a full octet. But also, the formal charge of -1 kind of gives it away. Because in order for oxygen to have a formal charge of -1, it needs 6 unshared electrons and plus the 1 bond that it has. And so this is an example where we have an anion, and usually with an anion, we start where the charge is with an arrow. We push that electrons away from the charge, so we're pushing electrons to some other location. So one thing that we could do is take a pair of the electrons, say here, and push them into the adjacent bond. So if we draw what that's going to create, well, let's not go that far yet. Let's just put single bonds everywhere. What that's going to do is take one pair of electrons off the oxygen and push them down to make a double bond. And we can't just stop there, because if we did just stop there and had the other double bond right there, See where I drew that second double bond? We got a problem with that, don't we? And that is we have a carbon with 5 bonds, which is too many for carbon. So we're going to not do that. We're going to pull that off. And so we're going to take the electrons in the next bond and push them along too. And we can't stop there either because that's going to make another carbon with 5 bonds. So we have to keep kind of pushing these electrons down the row. And let's stop here and we'll place them onto the nitrogen. So that means we're going to have a double bond here. We're now going to have 2 lone pairs on the nitrogen. And that's going to give the nitrogen a negative charge. And you know it's negative on the nitrogen because the nitrogen is, if you calculate its formal charge, it has 5 valence electrons. -4 for the 2 lone pairs, -2 equals -1, which is the charge that we put on it. So that's another resonance structure of this. Do you see any other possibilities for resonance structures here? Yeah?
So double bond in the ring rotate and you put one of the lone pairs back into the nitrogen?
Double bond in the ring rotate.
Like, does it move down to a different carbon?
Oh, down in one of the bottom positions.
Yeah.
You can't actually. And the reason is these carbons that are down here, and sometimes this can help you with your structures. All those hydrogens that you see there are sp3 hybridized. And if a carbon is sp3 hybridized, you can't push electrons to it or take electrons from it because it's what we call saturated. It's 4 bonds, it's already got its 8 electrons. And the electrons that are in sp3 bonds are not mobile like the ones that we're pushing around here. So you can kind of forget CH2s and only deal with the sp and the sp2 carbons. That's what we have here. The other possibility, and I'm going to start from the right-hand structure, is if we push those electrons back, we could instead park the electrons there. Where if we drew that structure, we have a double bond to oxygen. It still has its 2 lone pairs. The nitrogen double bond is back. It's only got 1 lone pair now because it used 1 to make that new bond. And the pair of electrons that was in this bond has moved on to that carbon. So we also have a pair of electrons here with a negative charge. So these are 3 resonance structures. What kind of arrow do we use for resonance structures? Double-headed, single line. Yeah. Single line, double-headed like that. Could use them all in between the 3 structures. Not to be confused with this kind of arrow, which is used for what? Yeah, that's an equilibrium one here. Reaction is just sort of like a straight arrow. We also have curly arrows. What's a curly arrow mean? Yeah, movement of an electron pair from where the arrow starts to where the arrow points. Of these 3 resonance structures, which do you think is the most important contributor? Top left. Because we have a negative charge on an oxygen on the left, or top right is nitrogen, or the bottom one is a negative charge on a carbon. And you want the charge on the atom that can handle the charge the best. So in this case, because oxygen, nitrogen, and carbon are all in the same row, they're all the same size, so you put it on the most electronegative atom in that case. All right. Do you want to see another resonance, or are you good with resonance? Yeah?
This article, it is a resonance question.
Okay.
When you get a question that says draw resonance structures, when do you stop? There are some that could just cycle forever.
In some cases, there's a lot of resonance structures you can draw, right? And again, when we make tests, I don't like to leave things that are open-ended and can have a lot of them, because usually there's a small number of ones that are important and a large numbers of ones that are not important. And I can show you what I mean by that. If you have a molecule that looks like this, which is ethene. You might look at this and say, it doesn't have any resonance structures. Well, technically, you can draw a bad resonance structure, which makes a carbon with a plus charge, a carbon with a lone pair, and a negative charge. So usually what we do with resonance structures is we only want the ones that make sense, that are actual contributors. Like in the previous example, I think all three are contributors. They're all good. And we tend not to give examples that have crazy numbers of possibilities. But again, I like questions that have a limit. So it says, draw 2 resonance structures, or 3, or 1, or whatever would be something like that.
Actually, the second part of the question I had was, there was a couple of questions that the answer was, it's not possible. So,
So there's no resonance structures. Yeah, and so that's true for some molecules. So if you have something like carbon, hydrogen, 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 C, H, H, F, 1-fluoroethane. This doesn't have any resonance structures because there's nowhere to push any electrons to or from. I mean, you could start on the fluorine and you could try to push them in, but you can't push any electrons to a CH2 because it's saturated already. It can't accept any more electrons to it. It's already got 8, and they're in sp3 bonds, which can't move anywhere. Yeah, does that make sense? Yeah, the resonance structures are tough when you first start getting them. And when you see lots of examples of them, they get kind of easier and easier. And definitely repetition and practice for these things makes things easier. That having been said, I'm going to give you some more repetition and practice. I'll give you one more example. The last example I gave was an anion. Let's do a cation this time. We can do something like, let's do a 5-carbon ring, the double bond, an O, a methyl, and a plus charge. So first thing I like to do is draw in lone pairs. Where are the lone pairs? On the oxygen, and it does how many? 2 pairs, yep. So let's put 1 pair here, 1 pair here. Draw the electrons nice and big, hopefully they're visible. And we have a positive charge. So generally what we want to do is take electrons and push them towards a positive charge. And we take electrons starting with electrons that can move. So the only ones that can move are electrons that are already a lone pair. They can move sometimes. Or electrons that are part of a double bond or triple bond, a pi bond. So this positive charge, luckily, has a pi bond right beside it. So what we can do is take those electrons and just pop them over like that. And just really closely notice where I put my arrows, that it's starting in the middle of that CC bond. So it's starting where the electrons are. It's not starting at an atom. It's not starting at one side or the other. It's right in the middle. And it's going to the middle of the next bond. So that would give us a structure that looks like this. And now the positive charge has moved over here. And how do you know the charge is there? Well, that carbon that has the positive charge on the right structure used to have 8 electrons, used to have 4 bonds, a double and 2 singles. But now we just took electrons away from it. And when you take electrons away, they get a positive charge. So the formal charge on that carbon is now +1. It's got 3 bonds, 6 valence electrons, and that gives it a charge of +1. Now, is there any other resonance forms for this? Remember, what we're looking for is an adjacent double bond or an adjacent lone pair.
Double bond on the oxygen and carbon.
Yeah, put a double bond between the oxygen and the carbon. So what if we took a lone pair off the oxygen and put it there? And again, I'm pointing directly to the bond. So it means it's coming down and becoming a bond between the oxygen and carbon. So that gives us a structure that looks like this. We haven't done anything on that side. We took a pair of electrons down. That oxygen lost a lone pair because that lone pair became the bond. That carbon is neutral again because it's got his 4 bonds again. It's got full 8 electrons. But that oxygen lost a lone pair, and so if you look at the formal charge on that oxygen, it has 6 valence electrons minus 3 bonds minus 2 electrons. The plus charge is now up here on the oxygen. So one thing to be very careful of when you're drawing resonance structures, the total charge on every structure has to be exactly the same. You can't change the charge when you go from one to the next to the next. And as your last step before you finish a structure, you should just double check what the charges should be on all the atoms. And then we could finish this off using our trusty resonance arrows. And we would say in the real world, this molecule, it's a single molecule, it's not 3 different ones, it's one molecule, and it's sort of an average of these 3 structures. All 3 contribute, not necessarily equally. In fact, almost for sure not equally. Just based on your understanding of chemistry, which of these 3 structures do you think is the biggest contributor? We'll call them A, B, C. I heard A, B, and C. So they all have a little bit of something going for them. So A is kind of good because you have a positive charge on an atom that's not very electronegative. B, same story. It's also on an atom that's not very electronegative. C, it's on oxygen. We tend not to like positive charges on electronegative atoms like like oxygen. But C has something else going for it that the other 2 don't. C is the only one where every atom has a full octet. Right? And it actually turns out that that means C is the best contributor. That having a full octet on all the atoms is a more stabilizing than having positive charges on electropositive atoms like oxygen, like carbon. So I would say all 3 of these are probably important. What the exact percentages is I could guess and say A and B are 25, 25, and C is 50, but we can't do those calculations in our head. We just say C is probably the best because everything has a full octet, but they're all important because they all have something going for them. The real structure is a blend, and real molecules love spreading charge out over as many atoms as possible. So it wants A and B to be in the picture because they put some charge on some different atoms. That's resonance for you. What else would you like to know? Yes?
Can you go over liquid-liquid extraction and how you separate 2 molecules?
Sure. So that's in the subject of acids and bases, and it's how you separate a mixture of 2 molecules using liquid-liquid extraction. Yes, so I'm going to answer your question directly because what I was thinking in my head is, do I want to go back and do a more general acid-base thing? But I don't think I have to. And we can later, but I think I can answer this without doing that. So usually when we do a liquid-liquid extraction to separate 2 things, what we're trying to do is separate a mixture of 2 molecules where one is soluble in water and the other one is not. Okay? And the best way to make something soluble in water is to put a charge on it. Make it a positive charge or a negative charge. And it really hates being in a nonpolar solvent and really loves being in a polar solvent like water. So almost always what we ask you to separate are 2 molecules where one of them can either gain a proton or lose a proton to get a charge, which makes it go into the water layer. So I'll give an example. Let's say we look at this molecule. which is cyclohexanol. And we're going to compare it with it looks similar, but it's not the same thing. This one, which is phenol. Okay. So on Moodle, you should be able to see a pKa list. I don't know if any of these are on your pKa list, but there's 3 functional groups that you should know approximately what their pKa is. And the one on the right is one of those 3. That's a phenol. Can anyone tell me the pKa of a phenol? Yeah, roughly 10. So that means if you are at pH 10, 50% of that molecule is neutral, like it is there, and 50% of it is going to be the anion that looks like this, O minus. These are in equilibrium. These are not resonance structures because we've moved an atom away. Resonance structures are only moving electrons. So we use this equilibrium arrow. And if the pKa is 10, then you have a 50-50 mix of the neutral and the negative at pH 10. So what would you do if you wanted more of the negative one? Would you go to higher pH or lower pH? So if we go to a higher pH, let's say we go to pH 12. That's really basic, right? It's like 100 times more basic than pH 10 because each pH unit is a factor of 10 because it's a log scale. So a pH 12, it's going to be basically like 99.99% in the negative form, and on the OH one over there, like almost nothing. So what I would do if I was given a mixture of these 2 compounds and asked to separate them, the one on the left is an alcohol. Alcohols are really difficult to deprotonate. You can't really make O minus from an alcohol in water, but phenols you can. pKa of alcohols, by the way, if you have a strong enough base, you can do it, but it's like 16. And you can't get to pH 16 in water. You kind of max out the solubility of NaOH at like pH 14. So what I would do is I'd take these 2 molecules, I'd put them in a separatory funnel. Did you guys do that, lab? Not yet. So a separatory funnel is a funnel that looks like this. It kind of has a top, and it's kind of angled like this. And there's a stopcock, and there's a thing there. And you put your mix in. You put in a non-polar solvent, and you can put any non-polar solvent you want in. What's your favorite non-polar solvent? Ethanol. Acetone. So those are, I want really non-polar. Think about the lab you did with distillation. Cyclohexane, yeah, there we go. Something really non-polar is cyclohexane. Why is it so non-polar? It has no electronegative atoms. Acetone has a C double bond O, it's kind of polar. Ethanol can hydrogen bond. You want something that's not going to dissolve in water. And then we're going to put in here water. pH 12. Okay, and at pH 12, what that's going to do is turn the phenol into the O minus. The O minus is going to go into the water layer. So in there, you're going to have the O minus. And then in the cyclohexane, you're going to have the other one that has no charge. And then you can shake them up. They'll separate into their favorite layers. And then you can let one layer go into one beaker, the other layer into the other beaker, and now you've separated them. Would you like to see another example? Okay. Let's say you have this molecule. naphthalene, mothballs, mixed with this random molecule that has a nitrogen in it. What kind of functional group is this? Amine. Not amide. Amide has a C double bond O. Okay. Which one of these is pH active? Like you can turn into an ion with an acid or a base. It's the amine. And anyone know the pKa of an amine?
5. No, 10. 10 or 5.
So it's 10, but 10 is the pKa of the conjugate acid, right? So if you have the conjugate acid, it has a pKa of 10. So that means if you're below 10, it's going to look like it looks here. And if you're above 10, the base will pull off the H plus and you have a neutral. We don't want it neutral, we want it to be charged. So at low pH, acid will protonate the amine. It'll be charged, and then we'll want to go in the water layer. So for amines, basically, like here's the crib sheet for all liquid-liquid extractions. If there is a phenol, you want pH 12 or higher. If you have a carboxylic acid, you want pH, I'd say 7 or higher. And if it's an amine, you want pH, I'd say 8 or 7 or lower. And this is going to become a cation. And these two will become anions at those pH values. So what you want for the phenol and the carboxylic acid, because they're acids, they like to give away H+, to charge them, you need to put them in pH solution where the pH is a couple units higher than the pKa. Because if you go right to the pKa, you get a 50-50 mix. We want to push it all the way. So we go a few units higher. Phenols have pKa's of 10, so we want to go pH 12 or higher. Carboxylic acids have pKa's of 5, so we want to go 7 or higher. And amines, when they're protonated, has a pKa of 10, so we want to go 8 or lower. Keep it positively charged. And then if it's not one of those three things, it's just going to be neutral no matter what, and it's going to stay in the non-polar phase, the organic solvent phase. Does that make sense? Yes.
What's an example of a question you might see as
So maybe a question like this, where I might say, you have a mixture of this molecule and this molecule. What is best conditions to separate? And let's say it was a multiple choice question. And you had some choices. And one choice, maybe like A, you're doing a separation, liquid-liquid extraction. I'll just put L, extract, with non-polar solvent, let's say cyclohexane, and water, pH 1. B, same thing, pH 5. C, pH 10. And those are your three choices. Well, ideally, what would the pH be? Is pH 1 a good mix? No, because pH 1, this is going to be in its neutral form. So they're not going to separate. They're both nonpolar. They're both going to be in the nonpolar phase. What about pH 5? Still kind of too low, because the pKa of a carboxylic acid is around 5. So it's going to be like 50-50. Half negative, half neutral. So you might separate a little bit of it, but you're going to get a mess. So what you want to do is go to a pH that's higher than the pKa. At least 2 units. I mean, that's what, like 5 units higher, which is really no better than 2 units higher, really. Slightly better, but almost no difference. But that's, I guess, a kind of question you could get like this. And if instead of a carboxylic acid, it was a phenol, you'd want to go to a pH even higher than 10. And instead of either of those two, one of them was an amine, you want to go to a pH below 5, like 3 or less. Or no, below 8. 8, 7, 6, 5, 4, 3, 2, 1. All is enough to protonate the amine. So all these things are important when you get into biochem, because when you look at amino acids all have an amine and a carboxylic acid at a minimum, and some of them have also a phenol, like tyrosine, and some of them also have an amine, like glutamine. And a big part of biochem is understanding in a cell at pH 7.4, what do all those different groups look like? What's the charge total on the amino acid? And then if you build a protein out of those amino acids, what's the charge on the protein? And so the charge on the protein determines a lot of its properties. And so this is sort of feeding into what you're going to be doing in biochem, but at an easier level, because we only have one thing on the molecule we're dealing with. Just an OH, or just a carboxylic acid, or just an amine. We're not putting multiple ones on the same molecule yet. That comes in biochem if you stay and do biochem too. That make sense? All right. What else? Yeah.
The equilibrium between like the acid reactions.
Yeah.
Whether it sits left or right.
Right. Okay. So the question is how to deal with those questions where you're given an acid-base equilibrium and you're asked whether it lies to the right or to the left. Okay. And I think there's always an option too, like somewhere in the middle. I think that's almost never the right answer. It's always left or right. So if you have like 3 choices, just don't pick that one. So it makes it, what's your probability of getting it right then? 50-50? That's not bad. Okay, so I'll give you an example to start with. Let's look at a molecule like this. Plus let's do I have phenol on the brain, so we're going to do this one. Okay, so here we have an acid-base equilibrium. An atom moved, an H plus moved from one to the other. We have, therefore, an equilibrium arrow, not a resonance. So when you have an equilibrium like this, it's going forwards and backwards at the same time. Almost never do you have 50-50. You usually have either more of the products or more of the reactants. And if you have more products, it's shifted to the right. More reactants, it's shifted to the left. And what a system like this will naturally try to do is find the lowest energy, go to the lowest energy state that it can be in. And the lowest energy state is it wants to make the weakest acid and the weakest base it can possibly make. So every example of this that you will get, one side will have an acid that's stronger than the other side, and that same side will have a base that's also stronger than the base on the other side. And so you can answer it in one of two ways. You can pick the acids on each side and rank them, or you can pick the base on each side and rank those. I personally find it easier to rank the acids, so I kind of just forget about the anions. I just look at the cations. So we're comparing this acid to this acid. They're the neutral ones with an H+. So which of those two acids do you think is stronger? The phenol on the right or the acid that's on the left? Left one, yeah. It's a carboxylic acid. What's the pK-ish on that one? About 5. The one on the right is what? 10. The lower the pKa, the stronger the acid. Really strong acids have negative pKa's, like HCl is -6. So this is the strong side, and this is the weak, or weaker, I guess we'll say. And that means if you look at the anions, the anion on the right is also a weaker base than the anion on the left, because the weaks are always together and the strongs are always together. It's impossible to do it any other way. So all we need to do is pick which side is weaker, has the weaker acid or the weaker base, and the equilibrium is going to favor that side. It's going to want to make more of the things that are weak, because weak things are more stable. Because if they were less stable, they would be more reactive and they would be strong. So saying they're weak acids is basically saying they're less reactive. We could also say they're more stable. So this side is more stable. So the equilibrium is going to favor the right. Now this one was maybe easy because it's a carboxylic acid versus a phenol, and those are two of the three functional groups that you're supposed to kind of know what their pKa is, 10, 10, and 5. But let's say it's something else, something maybe a little more subtle. And I'll give you an example of something a little more subtle. Let's say we're going to do something like this. And that's going to be the left one. The right one is going to be similar. And then what we're going to do is react it with if there's ever a time to say, oh, it's kind of 50-50, this might look it, because they look very similar, these two structures. But what we need to do is the same thing. We pick the acid on each side and we compare them to each other. So we compare that acid against that acid. And we want to pick out which one's weaker. And we have kind of a 4-step process to figure out which acid out of the pair is going to be stronger than the other. The first thing we look at is the size of the atom the hydrogen is attached to. And there, the stronger acid is going to be the one that has the bigger atom. It's further down the periodic table. But both are oxygens here, so there's no difference. So we move on to the second criterion, which is electronegativity of the atom that the charge is on when you make an anion from it. In both cases, they're oxygen, so there's no difference. You go to the third criterion, which is there resonance possible if you make an anion? Both of these have resonance possible, so there's no difference. So then you go to the fourth one. And the fourth one is presence of nearby electronegative atoms. The acid on the left has a fluorine nearby, electronegative atom. The acid on the right also has a fluorine nearby, but a little less nearby. Right? The acid that you see on the right, because the fluorine is 1 carbon down, is going to be a little weaker than the acid that's on the left. And you could think of an even weaker one if you put the fluorine on the furthest carbon away. So, which side is the weaker acid on? Right. So this is weaker. They're going to be close, but it's going to be a little weaker. Which side is the weaker base on? Also the right. And you could look at that anion and say it's going to be weaker than the anion on the left because it has a fluorine nearby that can pull some electron density towards it. The other one also does, but it's further away. It's not as effective at pulling negative charge because it's like, you know what I mean? It's not going to be felt as strongly by the negative charge having that fluorine kind of nearby it. So the two weak things are both on the right. This means the right is going to be favored. So the equilibrium favors the right or lies to the right or something along those lines. Do you want another one of these? Let's do one more. Let's do let's use and that actually is a mistake. That should be O minus. So now we're comparing these two. And so what we want to do is compare the acids that are on both sides. The left has an acid like this. The right has an acid like that. There's different ways to approach this. One is you can say, well, one is an ammonium ion, right? It's the conjugate acid of an amine. So what's the pKa of the conjugate acid of an amine? It's 10. So we could say it's about 10. You could look it up on your table if it's there. And what about the one on the left? It's going to be around 5. Which one's stronger? Left is stronger, so it's going to favor the right. Okay? But let's say you don't remember the pKa's of these things. You don't have a table on your exam, so you just have to look at these and use your own chemical intuition to figure out which of these acids is stronger. Well, what we would do in that case is, again, take our list of the four criteria we use to judge which acids are stronger. First one is size of atom. And by size, I mean sort of which row of the periodic table the atom that's attached to hydrogen is from. I kind of think of it a little bit like I think of the hydrogen as being like your hand. And let's say you're grabbing a ball. And you have a ball that's the same size as your hand, like a baseball. You can grab a baseball really tight, and if somebody tried to rip it out of your hand, they'd have to pull really hard. You know, you could grab it and make a really tight bond. And then imagine going to a bigger one, like a softball. You can still get a good, pretty tight grip on a softball, but a little weaker. It'd be a little easier for someone to take it out of your hand. And then go up another size. Imagine a basketball. And you're trying to grasp a basketball. You have a pretty weak grip on that basketball because the size of the ball compared to your hand is too different, right? You can only get kind of a weak grab on, I mean, some people can't grab basketballs at all, but it'd be pretty easy for someone just to pull it right out of your hand. And then imagine the next step up would be like a beach ball, even bigger, you know? So a hydrogen that's on a small thing or something that's approximately the same size, like fluorine, oxygen, nitrogen, carbon, anything in row 2, nice strong bond, and it's kind of relatively hard to rip that hydrogen away from the atom. You go down a level, it's like the softball, the bond gets weaker, it's easier to pull that hydrogen off, and you go all the way down to something like iodine. Iodine's gigantic. It's like a really weak bond to iodine, HI is a really, really strong acid because that bond is so weak. So that's the first one, size of atom. And what we're comparing here is a hydrogen attached to an oxygen or a nitrogen. Oxygen and nitrogen are side by side on the periodic table. They're effectively the exact same size, right? So the size of the atom doesn't matter in this case. So if you're comparing two atoms in the same row, the size is not different enough to make a difference. 2, then, we look at electronegativity. What's more electronegative, oxygen or nitrogen? Oxygen is more electronegative, so charges prefer to be on oxygen compared to nitrogen. So that means it's going to be easier to make an O- than it is to make an N-. So what we would predict, I guess it's not even going to N-, it's going to N neutral, isn't it, in this case? But still, oxygen here makes the acid that's on the left a stronger acid because it is more electronegative. Okay. It also has resonance, which is the third one, and the fourth one is an electronegative atom nearby to help out. It's got that too, so it's got kind of a lot going for it. All right, how are we doing with acids and bases? Pretty good? We're ready to move on? We can go back to it. What else would people like to... I got this one here. Yeah.
For the assignment for question 6, the very last one, where it says number of signals, I can't figure out a mirror plane on that.
Okay, let me pull this up because I don't have it just handy in my memory. Okay, so we are looking... No problem. Okay, assignment. This would be assignment 4-1. The last one.
The very last.
The very last one. It has a structure that looks like this. So we're looking for how many signals there are. The mirror plane on this one,
Is it right down, like,
yeah, it's like horizontal, kind of like,
so we ignore the ring flips inside?
yeah, so this one is a cyclopentane. And a cyclopentane, it doesn't really have a chair. It kind of have an envelope, but it kind of flops.
So it's gonna be symmetrical.
Yeah, and you could do the same thing. Whenever you have a ring like this, always assume they're just flat and they're not a chair or a weird structure. Because anytime you have one of those chairs or weird structures, they're flipping back and forth really fast. And
So that
the NMR just sees a blurred average. Yeah, so it sees them as if they were flat, which is a weird way to think, but it's not fast enough to see each individual conformation. So this one would have A, B, B, C, D, E, E. That makes sense? Which I guess, what's that, 5 signals? Any more questions? Do you have one? Yeah.
Yeah, kind of going off of like that NMR thing.
Yeah.
Can you talk about the theory on like the thing about shifting to the left, like something with like when you look at the spectrum?
Yeah,
That theory?
sure thing. So when you have an NMR spectrum, it looks sort of like this. The units we have are ppm. On the very left, we start at 0, and we go to like, I don't know, like 220 or so. And let's put right in the middle, 100, 150, 50, like that. And so the first thing that determines where you find a signal is its hybridization. So usually somewhere in this part of the spectrum is where you find sp3. And if there's something electronegative near that sp3 carbon, it's more to the left. And if there's not, it's more to the right in that zone. Okay. The next one would be a carbon that's either in an aromatic ring or in an alkene, like a carbon-carbon double bond. And they go from like around 110 to around 160. These are like sp2cc carbons. So we call them aromatic, I guess. Or alkene. And again, they're more on the left if there's electronegative atoms, and they're more to the right if they are not near electronegative atoms. And then kind of up here in this range is where you find sp2 C double bond O carbons. And it's kind of split actually in half, where those ones are aldehydes and ketones. And then on the other one, more to the left, you have carboxylic acids, amides, what else? CO esters. Basically, if it has an atom attached to the carbonyl carbon that has a lone pair, it'll be in this part. And if it doesn't have an atom with a lone pair, it's in this part on the left. And then I guess in the middle here is where you find SPs. SPs are kind of rare, but they're kind of in there. Do you want like the theory why they shift to the left or shift to the right?
No, that's fine.
Okay,
Thank you.
yeah. Because we're not going to test you on that, but if you're just curious, yeah.
No, this is good.
Okay. Yeah. Yeah, go ahead.
Can you go back to the signals on things that are obviously not symmetrical?
Sure. So just give some more examples. Yeah. All right, let's give an example of something that has no symmetry. I shouldn't say no symmetry. Some people will get mad at that. No planes of symmetry, no mirror planes. OH. Let's give this molecule. So there's nowhere you can draw a mirror plane in this molecule to make one half the mirror image of the other half. So each of these carbons is unique, A, B, C, D, E. And what we would expect for its spectrum, if this is 0, this is 100, is carbon B has an OH attached, so it's probably going to be down close to 60. It's going to be on the kind of the extreme end. So let's call that 60. And then A, C, D, E are going to be closer probably to 20. Something like that. So you're going to get 5 peaks, 5 signals for 5 carbons because none of them are equivalent. And carbon B is going to be kind of down to the left of the other ones because of the presence of that oxygen atom right attached to it. Let's say instead we go to this, which is a similar molecule. I just put a double bond in there. Well, again, there's no symmetry. It's still A, B, C, D, E. And so what we would see for this is B is still going to be more or less the same place. It's an sp3 carbon attached to an oxygen. Why did it go into that mode? Come back. That's going to be B. down, no, stop, don't do that. I think it's because these pencils, if you squeeze them too hard, like do the opposite of what you're doing, and I think I'm squeezing it too hard. No, oh my God, it's doing it again. All right, I'm gonna come down. There we go. You're gonna get two signals here for A and E. They're sp3s, they're not attached to electronegative atoms. And then you have C and D. C and D are sp2s, and they're not really attached to anything electronegative, so you're probably gonna find them close to 120. What about there somewhere? What if they have symmetry though? Let's look at some examples that have symmetry. Let's look at, let's use a cyclopropane. Cis 1,2-dimethylcyclopropane. Look at this structure for a second and see if you can think about how many signals you'd expect to see for this. See any planes of symmetry? Yeah. It's got a plane of symmetry that looks kind of up here. How many signals? 3. So we got A, B, and C, and that's B and C again. So even though there's 5 carbons here, you're going to see 3 signals. They're all sp3. They're all going to be probably somewhere 20 to 30 range. This is a kind of thing that can sometimes throw people off. Let's say you have this molecule, 2-methylpentane, 6 carbons. How many signals? It kind of looks like there's no symmetry, doesn't it? It's like there's no obvious mirror plane, you know? Like you might say, oh, look, well, maybe there's a mirror plane up there, but like part of it doesn't work in the mirror plane. But what happens with molecules like this is it's possible to draw a conformation of this that does have a mirror plane. You can take that carbon bond you have there and rotate it to kind of come up with something that looks like it's coming towards us, and then this kind of coming towards us too. You know what I mean? Like you're kind of taking that flat part and rotating it up, so now there's a mirror plane. An easier way to sometimes remember that than try to rearrange these things into conformations with mirror planes is just if you have a molecule like this and you have a methyl and a methyl on the end like that, and you could rotate them to exchange them with each other, you know what I mean? You can rotate them, then they're going to be the same, and it's going to be A, B, C, D, E. It's going to be 5 peaks. Same as if you have something like this. We have a T-butyl here. So I would go A, B, C, D, E, F, F, F. The 3 carbons on the end, the 3 CH3s in the end are all the same. The 2 methyls on the other end are also the same. And then you just add up 1 for each of the carbons. What if we draw something almost the same, but not exactly the same? Do that. We added 1 CH3. That's increased the symmetry, because now the both ends look the same, don't they? Both ends are both T-butyls. And actually, this one will be A, 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 A. I swear I need to figure out how to lock down my pencil here. B, B, C, C. So that will only have 3 peaks. I remember a bonus question we put on a first midterm a few years ago. sometimes we put bonus questions on and it kind of combines a few ideas. And it was this. It was draw an isomer of C8H18 with 2 C13 NMR signals. Eight carbons, but there's got to be a lot of symmetry to make it only have 2 signals. And the answer to that one was this. Which is similar to that last one because you have A, B, and B. So that's kind of how you deal with chains, is you kind of look. Here's another one with a chain. See, I would look at that methyl that you see there, and I would say, well, it's carbon 3 on one side, it's carbon 3 on the other side. So this one and this one look pretty similar to each other. Can you guys see that red? It's clear enough. And then if you look at the two ends of the chain, they look the same, B and B, C and C, D and D, E and E. 5 signals in this one too. We can do rings. I know which one I want to draw. Cycloheptane ring. One, two, three, four, five, six, 7. Let's put a double bond in there. Let's put 2 double bonds, a carbonyl group, and 2 methyls. How many signals does this molecule have? 5? Let's see, we got 1, 2, 3, 4, 5. Yeah, we have 5. It has a plane of symmetry that goes right up the middle. And remember how we asked you in one of the assignments to draw a structure and actually draw it with the correct bond angles? If you draw these with bad bond angles and weird bond lengths and things like that, it's really hard to see the planes of symmetry because you're drawing something that isn't really close to the actual structure. So we can go A, B, B, C, C, D, D, E, E. 5 signals. Lots of symmetry in this particular one. Yeah.
Can you go up, there's a previous, keep going. So right there, on your left molecule, the C and D are different in the middle, but on the right they're the same?
That's right.
Why?
Because on the right, the end, which is like a 3 methyls, and on the right and the left, it's 3 methyls, the same on both sides. So you could imagine, let's say you are sitting right there and you're traveling along these bonds. There'd be no difference between C and C. They look the same.
Yeah.
They have the same distance from B, the same distance from A, kind of just working in. They're the same. Where C and D on the left side's different. The left side only has 2 methyls and the right side has 3.
I was just looking at the carbons in like isolation.
Yeah, so the carbons actually are a little bit different depending on what's, you shouldn't just look at them just in isolation on their own. Yeah, it's the overall, yeah, they do look the same and they probably aren't going to be very different in the spectrum. They're probably going to have peaks close together, but they will be a little different. Yeah. How are people with chair flipping, confirmations and stuff like that?
I was just going to ask.
Okay, let's do some of those. Those can be fun. Okay. So often what we'll do is give you what we call a flat structure, which looks like this. And we might put like, I don't know, something like that. And we might say, draw this as a cyclohexane chair and then ring flip it. And did you have to do one of these on your assignment? 4?
Yeah.
And we drew the cyclohexane for you, didn't we? We got a little tired of trying to interpret what people were drawing, so we put the actual cyclohexane there, and you have to put where the substituents go. Just like the game chairs, if you play that game. It's kind of fun. All right, so what we want to do is draw a cyclohexane chair. And that's my attempt at a cyclohexane chair. And I think what we even might do on the assignment is number the carbons and put something like 1 and 2. They're numbered. Yeah, we like to do that too, just because it reduces the number of possibilities of answers we see and speeds up marking. I love fast marking. Yeah, so if I can that's when you asked before, like list all structures or list all possible. I don't like those questions. I like ones list 2, and then it's kind of easier that way. So here's how I'd approach a question like this. I would go to the structure up above, and I would look at the substituents. There's a methyl on carbon 1 and OH on carbon 2, and I'm going to label those substituents as either being up or down. Those are my 2 choices. If it's wedged, it's coming towards me, it's up. So the one on the left is up. The OH has the hashed bond. That means it's going back into the page. That one's down. Okay. So then we're going to go to our structure down below and look at carbon 1. Carbon 1 is going to have 2 bonds coming from it. It's going to have an axial bond and an equatorial bond. The axial bond is straight up, and the equatorial bond is going to kind of be to the side, but it's going to be parallel to the line that's 2 bonds away, which is this one here. Those are parallel. We're going to go to carbon 2 and draw those 2 bonds. Carbon 2 has an axial that's down, and then it has a bond that's over to the right. How do I know that carbon 1 is one that's up and not one that's down? The way you should look at it is every one of those carbons has 2 bonds coming towards it, and I think of them as like an arrowhead. And if the arrowhead is pointing more up, it's going to go straight up, and if the arrowhead is pointing down to that carbon, the line coming from that should go down. Yeah, Isaac.
So the peaks go up and like one's pointing down, go down?
Yeah, so like carbon 2, I see carbon 2, that's like an arrowhead coming down. So that means the bond coming from carbon 2 should go down, straight down. This is sort of an arrowhead that's sort of going up to me, so it's up. Yeah. And they alternate up, down, up, down, up, down as you go around the ring. So then all we need to do is go to carbon 1, and that CH3 we said was in the up position. So we're going to look at those 2 bonds on carbon 1 and decide which one of those is up and which one of them is not up. The up to me is the CH3 up here, right? And what's the other one? What should be on this carbon here? Well, that one's just a hydrogen, right? We don't draw the hydrogens, but there is a hydrogen up there. Now on carbon 2, the OH we said was down up above. So we're going to put it on the position of those 2 that's more down. And that one's going to be the OH, and the hydrogen is up here. Right? So we're going to look at those 2 positions on carbon 2, label the equatorial one up because it's more up than the other one, which is definitely down. Okay. So when I say up and down on that top structure, it doesn't mean axial equatorial. It's just up relative to the other thing that's attached to the same carbon. Now we got to do a ring flip. So what we're going to do is basically for the cyclohexane chair is draw its mirror image. And again, I don't have very good artistic skills, and if I can do it, then everyone in this room can do it. There we go. That's my attempt. And carbon 1 kind of got pulled down. So this is now carbon 1 in here, and carbon 2 is this one over here. Now carbon 1 looks kind of like an arrowhead pointing down, so that means the axial hydrogen or bond on carbon 1 is down, and it's going to have an equatorial one that's parallel to the bond formed by carbon 2 and carbon 3. Now carbon 2 is an arrowhead pointing up, so it's going to have an up, and then it's going to have an equatorial one that's going to come out kind of this way. So looking at carbon 1, I would say that it has an up and a down, right? So whatever we drew on the left, the CH3, which was up on the left, it's got to be up on the right as well. So let's do that. Let's get rid of our up and down, and we're going to put CH3 and H down here. And then we're going to look at carbon 2. Carbon 2, the down one was the OH. This would be the down, oh, come on. Down one is OH, and the up one is a hydrogen up there. So that would be the ring flip form. These are in equilibrium. Why aren't these resonance structures? Yeah. Resonance structures, you don't touch atoms, you just touch electrons. But these ones, we're moving atoms around. We're changing bond lengths and bond angles and things like that. We're flipping things from being axial to equatorial. These are not different molecules. They're just different conformations of the same molecule. Yeah?
So when you do a ring flip, what stays up? What was up stays up, and what was down stays down?
When you do a ring flip, anything that was, yes, so what stays up, and what is down stays down. But what was axial becomes equatorial, and what's equatorial becomes axial. Question. Which one of those two conformations do you think is more stable? Yeah, it's going to be the right one. And that's because it's got both groups equatorial. Right? And the one on the left is bad because both are axial. Yes?
So on the midterm, are we going to have to like draw it in ourselves, or will you give us like similar to the assignment?
It's probably going to be similar to the assignment. I can't answer it for sure because we haven't finished putting it together yet. And I'm only 50% of the voice on there because Terry is putting half and I'm putting half.
Yeah.
But our pattern in the past and our history and what we're almost likely for sure going to do is if you give you a question like this, we give you the template. Yeah. What I'm going to ask you do, here's the common mistakes people do on these templates. Okay, if you have, I don't know, it's not great, but you know what I mean. Where we have here an axial and an equatorial, what I'll see people do is put a bond right there. Like exactly dead way, halfway between the axial and the equatorial. And that's all they'll put. So it'll look like this. And I don't know why. I don't know if it's because they don't know if it's axial or equatorial, so they're going to put it in the middle and hope I give them the benefit of the doubt. Right? But it's definitely not in the middle. It's going to be either axial or equatorial. It's definitely not going to be halfway in between. So what I drew here will be incorrect. It would be a little more correct if you like put a hydrogen down there, so at least it was obvious that it was up and not down, but then you get half points. But to really get it correct, I don't even like looking at it there. Up. Like that. Vanessa.
Yeah. Is it more? Are the structures more stable when they're both equatorial? Because it's just like in my mind, I can imagine that to be more stable. But is there more of like a
Scientific explanation?
Yeah, like more of like a formal reason?
Yeah. So the formal reason is the axial hydrogens that are on carbons like 1, 3, and 5 sort of start to occupy the same region of space, and they get kind of crowded up there. So there's not much room on the axial positions, and so you get, it's called van der Waals strain. That's what you get. Yeah.
What's worse again, to have a methyl group or a chlorine?
Chlorine.
Like if you have.
Yeah. That's a shade of gray we are not going to enter. Because it is true that sometimes you can have two substituents where one is axial and one is equatorial, and you generally want the larger group to be equatorial.
Yeah, so you would put the chlorine axial.
Well, is chlorine bigger than a methyl?
Well, I guess it's a.
I would call that one a toss-up. Fluorine is definitely smaller than methyl. Ethyl is bigger than methyl. Isopropyl is bigger than ethyl. And T-butyl is the biggest one we have. Chloro is like, it doesn't have any atoms attached to it. So so the atom itself is bigger than carbon, but carbon has those hydrogens as well. So I actually don't know. I think methyl's bigger because of those hydrogens it has. But you can rest assured that question's not going to be on the midterm. Because if I don't know the answer, it's not going to be on there. Is it on the bonus?
It might be a terbutyl is what I'm trying to say.
Okay. If you see a terbutyl, that's going to be the biggest no matter what. You say it's on the bonus of an old midterm? On the bonus assignment. Okay. Oh, you have it right there as a piece of paper. Let me take a look.
That's a terbutyl.
Oh, that's an isopropyl. Yeah. So isopropyl is large. Once you start to get alkyl groups that have like branches, yep, no problem. Yeah, if you have an alkyl group with branches, that's going to win. That's going to win. Chloro is like, it looks big because it's a row down, but it's kind of compact because it doesn't have any other things attached to it. So, yeah. I'd go by degree of branching when you're talking about size.
Why is it isopropyl? Just because it's one?
Okay, so that thing that's hanging off has 3 carbons.
That makes it so it's like the propane.
Propane,
Add the YL at the end because it's branched.
propyl, and isopropyl is a non-IUPAC name. What iso means is that it's attached by carbon 2 and not by carbon 1 to the ring. You know what I mean by that? Like if you have, let's say a cyclohexane like this, I'd call that a propyl group.
Yeah.
But this one, I would call an isopropyl group because it's still 3 carbons, but it's attached on carbon 2. Okay, that's a non-IUPAC name. That would be a 2-propyl group would be the IUPAC name for it, and 1-propyl group would be the other one. Yeah.
How much naming are we expected to?
I would say that naming is a very low emphasis on this midterm. Again, I can't give you an exact thing, but we tend not to really test it much. There might be like a question on a midterm or something like that, but I wouldn't go too far down that path. Yeah.
So the last assignment that we had, it was the cyclohexane draw cis-1-bromo 2-chloro-cyclohexane. My problem was, where do you put do you start up or start down with the constituents?
Oh, so the answer is you can start with either.
That's
Yeah.
the conclusion I came to, but I wasn't sure if I was including that.
Yeah, so if you put them both up or whatever, you would draw one ring flip and then you'd flip it. Or if you put them both down, you would have started from the other one and flipped it back to the first one. Yeah,
So it doesn't really matter, just as long as they follow the cis or trans.
yeah, exactly. Yes,
I have a question on Newman projections.
Newman projections, yeah, I was expecting these to come up.
Can you have 2, like, of the circles in one?
You technically can. But I don't think we ask you those things.
Okay.
So I'm going to show you something that's going to blow your mind. Mine's already blown. Cyclohexane. We all love cyclohexane. If you look at this bond here and this bond here, they're parallel to each other. Some people draw this with Newman projections, because we talked about the chair as one way to draw it. Some people draw it like this, where this carbon, we'll call that 1 and 3, are two back carbons. And then this would be 2, 3, 4, 5, 6. And then 4 and 6 are in the middle. And you get how do you like that one? And then we have your axial, you have your equatorial, like I guess it's possible to make a Newman projection where you do something like this. And kind of show two centers at once, but we're not doing that. You don't have to worry about there being two in one. We only just are interested in one bond at a time.
Okay, so if you're branching something off it, can you put like CH2 and then CH3?
Yeah.
You just like condense it?
You can condense it, or you can draw the actual bonds if you like. So yeah, if you have something like this, say, and you have like, and 1, 2, 3, and we say you're looking down the 2, 3 bond. So what that means is your eyeball is right here, and you're looking down the 2, 3 bond. That means carbon 3 is the behind carbon. Behind is a big circle. The front carbon is carbon 2. And looking from that angle, who's that in this room? We'll make the hair longer so it's not me. Got curly hair. So carbon 2 is in front. From that vantage point, going straight down would be the CH3. We could either write the CH3 out, or we could just leave it as a line. If it's a line, it's implied that the end is a CH3. It's got a fluorine on the front carbon going off to the left, and off to the right would be the hydrogen. Now, kind of going away from you towards the back on carbon 3, remember we have kind of here, I don't really like how that looks. I'm going to erase the 3, and I'm going to put a hydrogen and a hydrogen. So on carbon 3, which is this round one, we have a hydrogen and a hydrogen. And on the back, we have a 1, 2, 3, 1, 2, 3. And on carbon 3, we have 2 methyls. So you could draw it like that, if you like. Yeah?
Is it inconvenient if we go back to chairs?
Nope.
I just wanted to do like 1 or 2 more examples of like comparing like the stability.
Okay. Yep. So let's say I gave you a question that looked like this. And I said, which of these two is more stable than the other? Well, in order to figure that out, you need to draw the chair structures. And so we're going to start with the left one, and it's going to have 2 chair structures. And we can go like, let's call that carbon 1, carbon 2, carbon 1, carbon 2. Carbon 1 has an up and an over. Carbon 2 has a down and an over. Carbon 1, which group is up? The isopropyl or the hydrogen? And this has a hydrogen as well. I would call this up and this down. CH3 is up, hydrogen is down. So we go over to our handy structure here. And what we're going to do is put our T-butyl up and our hydrogen down. And the other one, the up, is the CH3, and the hydrogen is down. And you have to always draw that hydrogen in. Like right here, where I have a hydrogen and a hydrogen, if you just left a stick there, that means it's a methyl, right? So you have to draw the actual hydrogen. This has a ring flipped form, where the up is still the isopropyl, the hydrogen is down, the methyl is now up, and the hydrogen is over. So that's the left-hand structure. Which of those two structures do you think is more stable? That's the right, I think. Your point, yeah, I'm reversed from where yeah, so it's going to be the right one because the larger group, which is the isopropyl group, is equatorial. So this one is more stable. That's not the question, though. Question was, which of those two isomers was more stable? So we got to do the same thing for the right one. And I would say that this group is up and this one is down. Okay? So we're going to take this and we're going to move it. Too much is coming with it. I'm going to redraw it down here. Okay, so that's the molecule. We called this one up, this one down. So let's draw our first. That's 1, 2, 1, 2. Carbon 1 up, we have a T-butyl, down a hydrogen. Carbon 2 up, we have a hydrogen, down is where the CH3 is. And when you get good at these, you can actually do them really quick. And then we can, on the other side, draw the mirror image. 1 is down, and then this one is now carbon 2. So the up is still the isopropyl and the hydrogen. And in this one now, the up is still the hydrogen and the down is the CH3. Equilibrium, which of these is more stable than the other? Right or left?
Right.
Yeah. Right has both of them equatorial. Left has both of them axial. This one's like the worst. So remember what the question said was those two molecules, A and B, which of those two molecules is more stable? Well, I would go with B here because B has a conformation, this one right here, where both of the substituents are equatorial. It also is the worst one, but it just can stay in the more stable conformation, which is on the right. The other one, which is these two, no matter what you do, always it has something axial, which makes this molecule less stable than the alternative. So it's not quite as good. So the more stable molecule, this one, because it has a conformation that has both things equatorial. Yes, question?
So whenever there's a wedged line, that means it's down, and when it's like...
When it's solid, like wedged, I call the wedged, this one here, and I'd call that one dashed.
Okay.
So the dashed is down,
Okay.
and the wedged is up.
Okay.
Yeah. Yeah. And you kind of can't go wrong. And to the question that was earlier, what if you drew it down and up instead of up and down? Well, that's just going to be the ring flip form. Yeah. Because, yeah, these molecules could all be flipped upside down and drawn. There's lots of different ways to draw these things, which is why we like to give you a template, because it constrains the number of possibilities that we get. Yeah. Yeah.
Can you quickly go over boiling points and how to determine what's higher and lower?
Yes. So boiling points, and I want to make a very clear distinction because they come right after one another in Unit 4. Boiling points and stability are unrelated. They're two completely different topics, two completely different ideas. Stability has to do with the strength of the bonds and how easy it is to break the molecule apart when you burn it. Boiling point is how well each molecule sticks to other molecules. And for alkanes, the only intermolecular force that they have is dispersion. And they're fairly weak, but what causes the dispersion forces to be stronger between two alkanes is how much contact surface area they have. So you can almost think of it like two pieces of Velcro. If you take like two balls that are made out of Velcro, like, you know, that game where you have the paddle and you catch the Velcro ball. If you have two balls and you stick them together with Velcro, they're like a tennis ball and a Velcro ball, they're pretty easy to pull apart. But if you had two strips of Velcro, same area, you know, but you press them against each other, so there's a lot of contact area between them, they're gonna be like really hard to rip apart. So molecules are a little like that too, that the more surface area they have, the better they stick to their neighbors. So for an alkane, the best way to get a lot of surface area is to have linear unbranched molecules. So something like this, be 1, 2, 3, 4, 5, 6, 7, 8. That's like a C8H18 alkane. It's long, linear. It's like a strand of spaghetti, if you want to think of it like that. And if you get like a bunch of wet spaghetti and let it sit for too long, they all stick to each other and you get this mess. Because when you boil something, what you're doing is separating the molecules from each other. You're ripping apart that Velcro. You're breaking those intermolecular forces. So if I took another isomer of this molecule, that's 1, 2, 3, 4, 5, 6, 7, and put a branch on it to make 8, that's going to have a lower boiling point because it's more closer to a ball, if you want to think of it that way. It's more branched, it has less surface area, it's not as long and skinny as it could be. And that's also C8H18, these are isomers. And we only ever really compare isomers. Let's say we add another branch. It's going to go down again. And I guess the lowest that you could make would be this. It's all branches. And this is like a ball, and this is like a hot dog, right? And so the longer and skinnier it is, the more surface area, high BP, low BP. Now, the difference might be 10 degrees Celsius. Like, it's not going to be dramatically different, but definitely it goes down a bit as you make them more compact. If you compare C8H18 with cyclooctane, what we find is the cyclic ones, I think they just stack nicely on top of each other. You might look at that and say, well, that looks really ball-shaped. And I guess it kind of does. It's a ring. But they, for whatever reason, nest really well together. And these have higher BPs, boiling points, than the linear ones. Okay. Now, stability is the opposite. Stability increases the more branches you have. So if you're heating your home by burning alkanes, like let's say you have a furnace and you feed in alkanes, for an equal amount of mass, this would give off more energy. or sorry, no, this one would give off more energy because it's less stable. The more stable one gives off less energy, which is the one on the right. And we don't really explain why. The reason is it's a property that they branched alkanes have called proto-branching that we don't explain or get into because probably none of us really understand it very well. The fact that it's more stable is an experimental fact, and that we can say with certainty. But there's a lot of theoretical chemists trying to figure out exactly the reasons why. To us, that's too much in the weeds. We want to just move forward.
So questions for those two concepts would be pretty cut and dry.
Should be cut and dry.
Which one's more stable, what has a higher performance?
Yeah, and that's basically it. And yeah, no problem. And really all you're going to be asked to do is count the degree of branching, like count how many branches it has. And we're not going to be, we try to make things really obvious. Like, for example, you might look at something like this versus say, oh, which one of those is more branched? They're kind of the same. They're not going to have the same boiling point. I don't even know the answer to this one. Like we don't like to fine-haired questions. We like the straightforward ones. And there's some big concepts that we've done so far in the first 4 units that are brand new to everybody. Like you've never seen carbon-13. You probably never really had to think about symmetry in this way. You probably never dealt with infrared or cyclohexane chairs or these conformations, even Lewis structures on compounds that have more than one like center. You don't really deal with. And so we try to test the big ideas. We're not trying to trick anybody.
So we just be responsible for building alkanes?
Yeah. I shouldn't say that. If I asked you to rank the boiling point of that and that, you should be able to do that.
And then you're just going back to IMS?
Yeah. Yeah. So you're going back to, the intermolecular forces, and alkanes are probably always going to be the lowest boiling because they only have dispersion. Yeah. Yeah. It could be tricky. And that's the thing is when you're studying these sort of things and we say, oh, this is more than this, they're general things, and you could probably find examples where it's not quite true for those 2 examples. And we just stay away from the gray areas. We're just trying to really focus in. The way a chemist's brain works is like, if someone makes a rule, the first thing a chemist tries to do is find something that breaks the rule. And so there's very few rules in chemistry that don't have any exceptions. We're trying to get the main ideas over. Yeah.
Thank you.
Yeah, no problem.
Has someone asked about Module 3 assignment question 2 yet? The one about ranking basicity?
We did not. I don't know about that specific question, but we did talk about that a little bit. But you can ask a question for sure.
Would you be able to go over that question?
Yeah, let me bring this up so I can see what you're asking. Module 3. Okay. Yeah, this one was one of the worst ones done when I graded them. O minus. O minus. F. O minus. Cl. S. O minus. Okay. So these are the 4 bases, and you are asked to rank them in order of strength from, I don't know what it was.
In order of strength for basis.
Increasing, yeah. So weakest to strongest. And there's 2 ways you could do this. One is you could add H plus to them all and rank the acid strengths, and the strongest acid is going to be the weakest base. Or you can just look at them like we have them. So all of these are O minuses, right? So we don't have to worry about size. We don't have to worry about the electronegativity of the atom where the charge is, which are the first 2 things we use when we're ranking acid strength or base strength. The third one is the possibility for resonance structures. Do any of these four have a possibility for a resonance structure? Well, yes, we can draw a resonance structure that looks like this. And this one does too, on the right. It also has a resonance structure. That's actually a damn good resonance structure too, because you're putting that negative charge on a sulfur. Would that negative charge rather be on sulfur or oxygen? No, I'd rather be on sulfur, because sulfur's down. It's big, right? The bigger atoms prefer to have charge. I know oxygen's more electronegative, but that's a secondary consideration to size. Size is the most important one. So if you go down one, it's going to be more stable on a bigger atom. But in any case, these two are definitely going to be more stable than the two on the left. So the two weakest, if we go A, B, C, D, C and D are going to be the two weakest. And A and B are going to be the two strongest. So of C and D, which one do you think is going to be more stable? Having a fluorine there or having a chlorine? Yeah, fluorine makes it more stable, because fluorine is like the rock star of electronegativity. So when you have the attached atoms, they pull electron density towards themselves. I just said that bigger atoms are more important, and chlorine is bigger than fluorine, but we're not putting the negative charge on this atom. It's just pulling some electron density through the bonds. And fluorine is really good at that because it's really electronegative. So the weakest of all is going to be C, weakest, and then D is the next one. And D has a chlorine, which is still pretty electronegative, not as good, but you're going to get the most stabilization from C and less so from D. Then we got A and B to deal with. What's the difference between A and B? B has 2 extra methyl groups on the carbon with the O minus. Okay, what do those methyls do?
They push the charge and make it less stable.
That's very good. So the opposite of fluorine. Fluorine pulls charge away and stabilizes the negative charge. These push more charge in where there's already too much charge. So the methyls make this one the strongest base because it has a lot of O minus, a lot of charge all in one place. It really wants an H plus to neutralize that charge. And those methyls don't help. They just keep pushing more. And so A is a little bit better than B. They'll be close, but A is a little bit weaker of a base than B. So I would go A, and then the strongest of all would be B. That's fair? No problem. Yep. Yeah.
It's easier to think about bases as acids, like just putting on the hydrogen.
Yeah.
And then, kind of reversing the strength.
Yeah.
Is that usually how you do it?
That's how I do it in my head. That's what I find easier.
That's helpful.
Because then you only have to kind of remember one thing, which is ranking acids.
Exactly.
And you don't have to remember 2 different systems of figuring it out. Do you want me to do this one again, where we make them acids?
No.
You're fine?
Yes.
Okay. Yeah. Cool. Anybody else? Unit 1, I'd say the big idea from Unit 1 is resonance structures and curly arrows. The big idea from Unit 2, infrared spectroscopy and identifying functional groups. Big ideas from Unit 3 are ranking acids and bases, identifying which side an acid-base equilibrium favors, and how to separate two molecules with a liquid-liquid extraction. And then 3 is all about conformations. We do the Newman projections, we do the chair flips, and then we do carbon-13 NMR. So there's some symmetry involved there. Yeah.
I don't know if you had already asked earlier, or if somebody had already asked earlier, but what do we get with midterm again?
So you'll get a periodic table, and there is a data sheet that's posted on Moodle, and I think it's called IR C13 chart or something like that. And it's up close to the top, and it's a one-page data sheet that has a pKa table, and it lists a bunch of acids and bases. So you know how you're supposed to kind of recognize that a phenol and a carboxylic acid, what their pKa's are? Those will be in the table. Like basic versions of, like simple variations of those. All the peaks for carbon-13, like the peak ranges are in there, and the infrared peak ranges as well. So what I would recommend you're doing when you're studying is study with that sheet, because that's the sheet you're going to get. And it's going to be the same sheet you're going to get for the final exam. And I think for the final exam, it's not like we add more sheets. That's it for data. But we're not really doing stuff after this that requires you to have a bunch of data. Like you're not going to be using, yeah. So, yeah, that's kind of where we're at.
What did you say was relevant for the third unit?
Third unit was the acid-base stuff, was sort of ranking acid strength, ranking base strength. If there's an acid-base equilibrium, determining which side of the equilibrium is the more favored side. And if you have what was the third one? Liquid-liquid extractions, figuring out what pH the water needs to be to get one component to go into the water phase and the other component to stay in the non-polar phase. And that's an important, like, actual real-time skill if you're a chemist, because you do liquid-liquid extractions a lot. Yeah, Vanessa.
I had a question about, you know how we know the pKa for the carboxylic acids and the phenol and the amines?
Yeah.
So there's something different about the amines? Like,
Yes.
It's, okay, like say you want to separate it, you make the pH lower instead of higher. Why?
That's right.
Why?
Because for a carboxylic acid, it's an acid, so it loses H plus and becomes O minus. So you need a base. It needs to be basic solution. It needs to be a high pH to turn it into the O minus to make it water soluble. Phenol, same thing. OH, you lose H plus to become O minus. Once it's negatively charged, it becomes water soluble, and you need to go above pH 12 or whatever. For amines, though, what makes them different is they don't have an H plus to take away. They gain an H plus. They react with an acid to make a cation. So they need to be put in low pH. They need to be put in acid to protonate them, to turn them into a cation, because it doesn't matter if they're plus charged or minus charged. They just need to be charged to be soluble in water.
Because if it's in an acidic environment, there's lots of, in any acidic environment, there's lots of hydrogen.
Yeah.
So if it needs a hydrogen, that's the idea.
That's right.
Put it in acidic.
That's right.
Okay.
Yeah. And if you need to take a hydrogen away, you need to put it in base. Yeah.
Because there's almost like a lack of hydrogen.
That's right. Yeah. Exactly. Yeah. And when you get into biochem, you get these things called amino acids that look like this.
Throwing, someone just.
So with an amino acid, if they're in pH 7, then the carboxylic acid is COO minus, and the other part is H3N plus, because the pK is like 5 and 5 on the right and 10. So if your pH in the middle, you get this thing, which is called a zwitterion. Zwitterion is something that has a positive charge and a negative charge in the same molecule, overall neutral.
Ibuprofen.
Yeah.
That's fine.
You guys are troopers.
I'm just procrastinating another midterm.
Oh, really? What's the other midterm?
Principles of development.
Right, principles of kinetics.
I have microbiome tomorrow night.
I had that yesterday.
I'll take that.
Or no, I had that this morning.
Matt, thank you.
No problem. No problem. Has everyone got all their questions answered? You got, yep.
Dashes and wedges, when would you use them?
All right.
Just use them forever.
So dashes and wedges actually become super important in Unit 5. We use them a little bit in Unit 4.
Terry loves the dash and wedges.
Yeah, we all do.
Yeah.
They're awesome.
Sometimes I'm like, okay, there's lines here, but then there's dashes and wedges too, so.
Okay, yes. So why do we sometimes just use a line? And the reason is because if I gave you lots of examples tonight that look like something like this, and I just use lines, and I could have used a wedged and a dashed. The reason is if it's a chiral center, when we get to Unit 5, you have to use dashed and wedged
That's what we went over today.
to show if it's R or S. If it's not a chiral center, we usually don't bother with dashes and wedges because we're not trying to show whether it's up or down, because it could be up or down, because there's not really any difference. Yeah.
So not really.
It's not really a big deal.
Someone likes the geometry.
Right. So like when we get to cyclohexane, we use it there because we might do something like this. Right? And we have to use dash and wedge here to show they're both cis or both trans. But if you only had one thing on a cyclohexane, we usually don't use it. Because if you only have one thing, there's no chiral centers because there's symmetry through it. And it could be up or down, it doesn't matter because it's going to be both. Like if you draw the chair, it's going to flip back and forth and go up or down. So yeah, usually we kind of, we only, yeah. So I'd say the times when we absolutely draw the dashed and wedged bonds is when we have stereoisomers possible, like cis or trans, or R and S, chiral centers. Then it's really important to show them.
Or like geometry.
Yes. Yeah. Yeah. Yeah.
Do we need to know anything with diamines?
Diamines. I don't think so. No.
Just came up in the notes and I was like, I didn't really have anywhere else I saw them.
Oh. Oh, I think they were in the examples of, for like cadaverine. Yeah. They're just sort of examples of amines. There happens to be, there's nothing special about, there's just two of them, that's all. Yeah. Yes.
Are all of the units going to be equally weighted on the midterm?
Usually we try to, although some units are considerably shorter than others. I consider chapter 2 to be very short. It's like, what do you have to do? It's like functional groups, memorize the dozen or so we have, and then infrared, and that's it. I find 4, there's kind of a lot in 4. There's a multiple choice part and a written part. The multiple choice part is 25 questions that I wrote, and so those are quite evenly spaced over the 4 chapters. There's like 6 or 7 questions from each of the 4 units.
And you like straightforward.
I like straightforward. I really do. I don't like tricky ones. I don't like borderline edge cases. I like it's this or it's that. Yeah. And what I really like is if it's not only is it this or it's that, there's two reasons why it's this and not that. You know, those ones are even better.
That is such a difference from biology.
Is it? Yeah. And I think chemistry, I don't know, I feel like that the subject in chemistry it can be very, I don't know, it's intangible, right? It's we're trying to like understand this whole world that we can't see. And so we're trying to find the big ideas and clearly differentiate them. Yeah.
The material being discussed right now is not on the midterm.
What material?
The ones that we did like in class today. And
No, that's right. Those are Unit 5 stuff is not on the midterm. Yeah. It's a fun unit though. And it is funny too, because we kind of like really switch gears in Unit 6 away from structural things and more into chemical reactivity. Although we keep coming back, like we do these Newman projections and we kind of like leave them, but we come back and they become important later on. And the chairs do too. Because it turns out it's like one reaction we're going to do in like Unit 7 is elimination. And elimination can only happen on a ring if the group that's being eliminated is axial. And so in some ring flip forms, there's no reaction. And you have to kind of go through the ring flips of those when we get to them. So we are doing it in Unit 4, but we keep coming back to the things that we look at. And I feel like this whole course is laying the foundation. Like all the main ideas in organic chemistry kind of come in this Organic 1 course. And when you do Organic 2, there's not really a lot of new ideas, but we use those ideas and take it to a lot more examples. So for example, by the end of Organic 1, you'll probably learn about 20 reactions. And Organic 2, you'll probably learn about 70 reactions. And it's just more reaction, but the basic ideas don't change. It's all stability, resonance structures, conformations. It's all the same kind of thing. It keeps coming back. So you could argue all of organic chemistry boils down to two ideas. One is sterics, which is shapes and like how things take up volume and interact with other things that take up volume. Bulky things take up more volume than small things, and that impacts chemistry. And the other one is electronics, which is, we've talked a lot about that, how electronegative things pull electrons towards themselves. Resonance moves electrons and shares them delocalizes them and shares them between atoms. And basically everything that happens in organic chemistry is either because of sterics or because of electronics or some combination of the two. So I know that's simplifying a lot, like of fairly heavy stuff when it's new, but the more you learn about organic chemistry, the more it all just kind of comes into one or two ideas, which is, I don't know, it's kind of gratifying if you learn a lot about it.
Sure.
Yeah.
we trust you.
Yeah. I kind of think of like the sport like baseball. Baseball has a lot of rules, and the rules are kind of complex. And it must be a bewildering sport to learn when you're first put down. And let's say you learn by watching a game, and you're like, why is the pitcher leaving? Oh, they pulled the pitcher and they're pulling another pitcher. Okay, how come he only pitched 2 pitches and now he's gone? Oh, well, that was a relief pitcher. You don't put a relief pitcher and there's so many rules. But once you've watched 1,000 games, the rules are just like second nature. And maybe every once in a while, some weird rule comes out that you didn't know. But all the basic rules, they're just old hat. And so organic chemistry is like that. We're teaching you all the rules in the first course. And then once that course is over, it's like more games. And the rules, you see the same kinds of arguments again and again. Resonance, acid-base, stability, conformations. This group's big, this group's small, therefore this one's fast and this one's slow. Like all these things keep coming up again and again and again. So if you like what we're doing and you get the rules from Organic 1, you're kind of set. Go do more chemistry. Yes.
Could I ask you again to explain the difference between stability and reactivity and how stability impacts like acidity and basicity?
Yes. So I'm going to be careful with my words here, because when I say stability, what I'm talking about is energy. That something is, and stability is always relative. So when you say something is stable, you have to say stable relative to what? And so usually when we're comparing isomers, we might say, well, this isomer is more stable than that isomer based on heats of combustion at a lower energy. Generally, things that are more stable, things that have a lower energy than other things that are comparable, tend to be less reactive. They tend not to do reactions as easily. And that's true when you're looking at things like a base, for example. If you stabilize a base by spreading the charge through resonance or putting electronegative atoms to spread the charge that way, or putting the negative charge on a bigger atom, all these sorts of things that stabilize the base, stabilize the anion, make it less basic, make it weaker, make it more stable, make it less reactive, if you want to think of it that way. The reason I'm hesitant to use the word reactive is in chemistry we define reactive based on a rate. So something is reactive if it reacts quickly. And stability and reactivity, one is measuring thermodynamics, which is stability, and one is measuring kinetics, which is reactivity. So I don't like to confuse those terms because they're kind of a bit different. But in terms of a base, pKa is a measure of stability. It's a measure of thermodynamics. Delta G, all those things you do in first year. And the more stable it is, the less likely it is going to engage in a reaction with something else. Whether it's acid-base, whether it's really anything. And really what all molecules are trying to do is get into the most stable state that they possibly can. Whether it's through reaction or whether it's through going to the best conformation it can find. But at the same time, at room temperature, it has a lot of energy, thermal energy, that's just being kind of thrown at it. And so it's not always going to settle down to the lowest state because you're constantly kind of shaking it by giving it energy. So they're still going to go into unstable conformations sometimes. And they're still going to collide with other things. And they're still going to react. And sometimes they're going to react to make things that are less stable. May do endothermic reactions. But usually everything goes downhill. And that wants to be in the lowest possible state, as stable as possible. So when you have an acid-base reaction, it's going to favor products. It's going to have more products that are more stable. Yeah.
That makes perfect sense. Thank you.
Cool.
Would I be able to bother you for an IR spectroscopy question?
Sure, yeah.
On practice assignment 2, question 2, it's one of those questions where we're given 3 molecules and we need to identify the chart that they.
Practice multiple choice?
It's in the recommended extra practice assignments towards the.
Oh, those ones.
It's like buried all the way down. I'm so sorry.
Yeah, no, we put
It's like in the basement of the Moodle.
we put a lot of stuff here, don't we? Final exam information, no. I see some things that you guys can't quite see yet. Current test information, no. Recommended extra practice assignments, and this is assignment 2?
Yes, the second question.
Okay. A student recorded IR spectra of valeronitrile, valeraldehyde, and 1-pentanol, but he forgot to label them. And these are the 3 structures. A, B, C. The 3 spectra are below. Help him identify the compounds for A, B, and C. And then it gives 3 spectra that it's not going to be easy for me to get on the screen. Do you have a specific question, or do you want me to just kind of go through it?
I was hoping you could just go through it.
Yeah. So the main things I would look for these three compounds, for C, we have an OH. An OH would be the characteristic signal. Yeah, you get a big, broad, swoopy, broad peak. Usually peaks are sharp, but this one's not. It's kind of broad, and it comes at around 3,300 reciprocal centimeters. And that will be in your table. And the way it'll look, it'll be BRS, which stands for broad signal. Maybe it just says BR, broad. S means sharp, so I guess you wouldn't have broad sharp. That's what I would look for C. B has two kind of main features. One of them is this carbonyl group. Carbonyl groups always come around 1700. Could be 1720, could be 1750, but it's going to be around 1700 somewhere. Very strong signal that goes all the way to the bottom. So it's a very strong peak. It's a little broad, not as broad as an OH. It's not like razor thin either, though. It's got a good girth to it, you know? And you can see that in the third spectrum, spectrum 3, for that particular one, down at like 17, looks like 1720 in that one. The other thing aldehydes have, I'm not sure if Terry's section talked about this peak or not. It's called the Fermi doublet.
What?
I'm looking at it right now on spectrum 3. Fermi doublet, a CH that's on an aldehyde gives a pair of peaks at like 2700 and 2800. Two peaks that are like similar in strength, and they're how you tell an aldehyde apart from a ketone, because aldehydes have them and ketones don't.
So the aldehyde both is really sharp all the way to the bottom, like it goes all the way down and has the twin.
Yeah.
And that's the one in spectrum 2.
No, spectrum 3.
Spectrum 3.
So see the big one at 1720 that goes all the way to the bottom?
Oh yeah, just the little double.
And yeah, the little doublet, one half of the doublet sort of like is swamped by the CHs, by the sp3 CHs. And then the other one is the nitrile, and the characteristic thing is there, and it's at like 2200. And it's easy to pick out because nothing else comes there except for triple bonds, carbon-carbon or carbon-nitrogen triple bond, right around 2200 wave numbers. And that's spectrum 2. So that's a good question, because the three most easily identified peaks in IR are these three compounds. Those would be the triple bond, because it's in a region where nothing else can be found. The alcohol, because it's that broad singlet. And the carbonyl group in the aldehyde, because it comes at that big strong peak at 1720. Nothing comes there except for a carbonyl group. So you get good at identifying those particular peaks.
What did you call that again? A
Fermi doublet, yeah. Fermi doublet. Fermi, like, there's the famous scientist Enrico Fermi. I don't know if,
Fermi paradox.
what's that?
That's the guy who did the Fermi paradox.
Yeah. I don't know if he's the same guy that did the Fermi doublet. I mean, it's probably, but it's, yeah, pretty different to the other stuff that he does. But anyway, I'm not sure if Terry's section talked about the Fermi doublet or not.
That's the first time I've heard of it.
Okay. In that case, it's not going to be on the midterm.
I feel like that's a question
Yeah. Yeah. We do both go through each other's questions and make sure, because I would say we have 99% overlap between the two sections and what we cover. We're like very lockstep. This Fermi doublet thing is just it's sort of like one of those minor details. And every year, I think like I teach it and she doesn't. And we always talk, oh, okay, we'll fix it next year. And then we never remember to.
It's just a little fun fact.
Yeah, exactly. It's a fun fact. And if you go on to take structure determination, which is another course in chemistry in third year, 3523 is the course. You're going to learn about the Fermi doublet there, so may as well take one thing off your plate for your third year.
How do we tell the difference between a nitrile and a carbon-carbon triple bond?
Okay. Good question. A carbon-carbon triple bond and a carbon-nitrogen triple bond come in the exact same place. So you can't tell by the position the difference between them. This is the difference. CN triple bonds typically are quite strong because the size of the peak is related to how polar that bond is. So a CN bond is much more polar than a CC bond. That's not that helpful though, right? The one thing is carbon-carbon triple bonds, alkynes, come in two types. We call them internal alkynes, and that's when you have carbon chain on both ends. Or you can have terminal alkynes, where the triple bond comes at the end of a chain and there's a CH. So if you see a signal, so first of all, internal alkynes are weak, weak, weak. You might see a little like at 2200, and that's it. And you might not see anything. And that's because the polarity of that bond is like nothing. And so it can vibrate, and you might see a little signal, but you're not going to see very much at all. If it's terminal, though, it tends to be quite a bit stronger, and it's a little easier to confuse a nitrile with a terminal alkyne. But a terminal alkyne has a CH. So that infrared spectrum, I'm going to put two side by side. Start at the top. We're going to put, this is like 2000. This is 3000. This will be the nitrile. It has a big peak, typically at 2200. And you're probably going to have some CH stuff over here for alkyl CHs, sp3. If you have a terminal alkyne, you get that same peak. Usually it's not as strong, but still can be pretty strong, but hard to tell apart. But it also has that CH out at 3300. So what you're looking for is the combo of these two peaks to tell that it's a terminal alkyne. If it doesn't have the left-hand peak, it's a nitrile. If it does have that peak, it's a terminal alkyne. And if it's an internal alkyne, it's just going to be like a little nub up there.
But
Yeah.
the big peak on the left represents the SP.
SP, yeah. CH, stretch.
Why do they show up twice on the graph? Like, why does it show up as both an SP and as the triple bond?
The triple bond is a carbon-carbon bond, and the other one is a carbon-hydrogen bond. Yeah, so we can get the CH. And there's going to be other CHs there probably. There's probably going to be sp3 CHs, maybe sp2 CHs, but the SP is quite separate, quite strong, and really identifiable. The only issue with that peak at 3300 is it comes at the same place as an alcohol. But the alcohol's kind of a broad guy like that, not sharp. So it can be tricky, and if all you're going on is the table, it can be hard. Like if you've never looked at one and you're like, oh, I don't have to worry about this. We're given the table. The table can help, but like it can be hard to interpret. The table is just like functional groups and numbers. But if you go through enough of these, there's not a lot of different combinations of peaks. It's like 12 functional groups that we see, and you can usually, I guess what I find is every year we try to come up with new questions on new midterms and things like that. And they always end up being variations of old ones. And so like when we get to the end of the course and you have all the old exams, this year's exam is going to be some rearrangement of all the last 5 years worth of exams. It's going to be more or less the same questions. But instead of a 7-carbon chain with a nitrile on it, it'll be a 5-carbon chain with a nitrile. It probably won't change the infrared spectrum. It'll look the same. Okay. But honestly, like a really good way to study this, it's important, I think, to go through your notes and really like try to like understand the theory and all that sort of thing. But like look at old exams. It gives you an idea of what we emphasize when we test things, what we think is important and what we think isn't or less important. And if you do like last year's midterm and then the year before and the year before, what you're going to find is this question was on last year's and the year before's and the year before's. It's probably going to be on this year's too, right? And so like an example, I can tell you right away, there's going to be a question where you're going to have to draw resonance structures. Every year we do that. And I can tell you, and when you start to look at more and more and more resonance structure questions, you start to see that they're all kind of the same. There's, instead of 3 bonds, there's 2 bonds. Instead of a nitrogen, it's an oxygen, but it's the same kind of arrow pushing, same kind of idea. And kind of when you practice enough of them, it's like you can't be tricked anymore. It's always the same. We're not trying to trick you, but you know what I mean? Like it really becomes second nature because there's only so many ways we can put carbon atoms together in a chain. Yeah. So what are some other things? There's definitely going to be a cyclohexane chair flip. There is every year. There's definitely going to probably be a Newman projection question where you have to draw down the C2, C3 bond. Like practice those if you see them coming on midterm after midterm after midterm. Like pretty well everything that we did, especially the things I've been emphasizing today from each unit, will appear on there. You will see a carbon-13 spectrum. You will see an infrared spectrum. You probably are going to be asked about isomers. You're probably going to be asked about stability of cyclohexane, chair flips. And this is me saying this without having seen a midterm yet, because I'm going to be making it, and that's what's in my head. I'm going to be making half of it, I should say. I also have office hours this week, Wednesday afternoon. So and the office hours kind of extend past 4 p.m. So if you're in lab, you can come after lab. If you can't come at all, you can email me and we can make an appointment. Set a time up. You can come ask your questions. I feel like one of the difficulties of this course is that we give you so much practice, right? It's sort of it's a good problem to have, I suppose. And I think some people feel like they have to do every practice problem we give you. But there's always people that no matter how much practice I give, they'll always come looking for more practice. So we just load the practice on there. And some people, the way they like to study is do an old test, check it against the solutions, correct their mistakes. Do the next test, correct it against the solutions. And then when they're done, they start at the beginning again, and then they make fewer mistakes each time through. And they don't look at the notes at all. They don't look at recorded lectures. They don't read the book. They don't do any of those kinds of things. They just drill the questions. And because our questions don't really change from year to year, that's an effective way for some people to study. It wasn't the way I studied as a student. I read textbooks, and that was really all I did, because I wasn't good at taking notes, so I didn't really have notes to go from. In my day, we didn't have PowerPoint slides. When I was a boy. Yeah.
You walked us the hill both ways as well.
It was pretty bad. Yeah. Yeah. Deep, deep snow. Pre-global warming. That one's actually coming true, isn't it? Not as much snow now. Yeah.
It was 28 degrees today and it's October?
I know, right? Wild.
I'm in the bathing suit.
Are you ready for a swim? I was thinking today, it's probably a better time right now to swim than June.
Yeah.
The water's probably nicer.
It is.
The air is just as hot.
It can be nice up until like the middle of June.
Yeah. But when it's done, it's crappy. Yeah. We could use still some rain though. We haven't been getting quite enough yet. Have you had enough organic chemistry for one night? Yes. Another question.
What are some common mistakes that you see a lot that you think we should be aware of? What is everyone getting marks docked for? How do we avoid it?
I find the first midterm, it's a little bit of everything. What I find going from the first midterm to the second midterm is the average drops from the first midterm to the second term. But some people do better. So if you're the sort of person that you get all the big ideas, but you're prone to making small mistakes, those people tend to do better on the second midterm than the first midterm. Because it's easier on the second midterm, I find, to like avoid mistakes, get everything kind of right. You know what I mean? But it's also easy to get everything wrong. Where on the first midterm, very rarely does somebody get 0 out of 10 on a question. You know, like there's always something right about it, and even if you miss some details, you're probably going to pick up some points. So what do people get wrong? I would say it's a little bit of everywhere, but I would say the biggest thing people get wrong on the first midterm is the small details. It's like curly arrows. Did it start at an electron pair and end where the electrons go? People will start from an electron pair, but point to an atom instead of pointing to where the bond should go, if it's becoming a bond. Another common one is when people are drawing zigzag structures, and then there's an alkyne. They keep the alkyne zigzagging as it goes. Alkynes are linear, so they should be 180 degrees. Drawing more than 5 bonds to carbon, you see that happen a lot in resonance structures. They'll push electrons, and they'll push electrons in where they can't go, and then there's 5 bonds to something. That happens sometimes. The resonance structures, I would say, is one of the trickiest things that people find from the first 4 units. The cyclohexane ones, it seems like people maybe struggle with it until they get it, and once they got it, they got it. It's fine. People, once they get it, they rarely trip up and make small mistakes. It's like, yeah, once you nail it, it's solid, I find. But resonance structures, you get people in graduate school in chemistry still messing up resonance structures. We actually hired somebody, we didn't hire them, but they interviewed to be hired externally as department head. They had been working for 20 years as a prof at a different university. And in his seminar, he started drawing a resonance structure for phenol. And he got caught up and he started doing it wrong, and then he couldn't finish it, and then just wiped it and kept going. So it's a skill that, yeah, it can be difficult. It can be difficult for sure.
What were the mistakes you said people made with the curly arrows?
Okay, so curly arrows always start at an electron pair, and they always end where the electrons go. So if you have something like this, and you want to make this structure, which is a resonance structure of it, how are we going to move those electrons? Well, you can look at that and say the oxygen has 2 lone pairs, and on the right it has 1. So a lone pair has moved. And where does it move to? It's moved down to make a double bond. So the correct way to do it, I keep like, and if I rotate my pen, then I can't squeeze it anymore. But if I rotate it back, I can. So I'm just bad with this. That's all. It'll take, yeah, I'll get it. So you see how I drew it here? It starts at the lone pair and moves to the space halfway between the oxygen and the carbon. An incorrect way to do it would be this. You see that? Where they're pointing to an atom. That's wrong.
We should go to the font.
Yeah. Yeah. Sometimes you see things like this, like, that's a minor mistake. Some people will go like this and make a structure like this somehow. Like, you can't do that. You can't draw an arrow, move electrons way far away. You can only move it somewhere close by, move it adjacent. You can move it to the next carbon, to make a bond. Or you can move a bond up onto the next carbon.
You can't like jump.
Can't jump. No. So if you had something like this, plus, and a bond over there, you can't go, oh, let's move that over there. Yeah, it's too far away. This has no resonance structures. But if we put that in, it does. This has resonance structures because you can move that over. So again, it's starting at not a lone pair in this case, but a double bond. It's right in the middle is where it starts, and it travels to the space halfway between the two carbon atoms. And so that would have this as a resonance structure. Carbon-carbon double bond there. And now the charge is over here. That was a bad double bond. Why did it move like that? That. And you can move it back and go back the other way. Those are the two resonance structures, back and forth. There's molecules actually that look like this. Long chains like this. Like thousands of atoms. And if you put a cation on one end, what you can actually do is have this sort of like all of them shift together, and then the resonance structure has a positive charge on the other end. So you can move charge along these chains really fast, and that's how you can conduct electricity. So you can make like organic wires that move charge through long chains like this. So you could. This won the Nobel Prize, by the way, in 1990. Ian McDermott, I think, for conducting plastics that do this sort of thing. Cool stuff. This is Nobel Prize week, isn't it?
It is. They announced the chemistry ones, I think, today, actually.
Oh, the chemistry one's out today?
Yeah, because I remember it might have been biology or medicine today.
Okay.
But
Yeah. Chemistry is like half the time goes to chemistry and half the time goes to like biochemistry. And I feel like lately it's mostly biochemistry. Because I feel like biochemistry is making more like huge leaps right now than chemistry is. Chemistry is sort of like a little more established.
The award winners today, they were able to identify the cells that control your immune system's ability to detect whether something's a bacterial cell or your cells.
Oh, cool.
And they're able to use it to regulate autoimmune diseases and like prevent your body from attacking itself.
Oh, cool.
So they won like $1 gajillion and like a big prize for that.
So like 20 years away from actually treating something.
Yep. And then, yeah, the time I need it, they'll have cured rheumatoid arthritis, hopefully, and all those things. Yeah, it's wild the advances they're making in medicine and biology right now. It's like skyrocketing. And it's kind of like where, like, I don't know, automobiles were in the 1920s, it's all of a sudden they're just, or computers were in the 1990s, just like such a rapid development.
Maybe you'll still be teaching here in 200 years.
I could be, once they cure that aging thing, right?
Just put your head in a jar.
That's right. Put me on like a robot body and I'll just like, yeah. That'd be kind of cool.
Why don't you have the Nobel Prize yet?
I got robbed. Actually, a Nobel Prize, if you look at the age of people that get Nobel Prizes, they're like often in their 70s. because usually what happens is they'll make a big discovery and they'll wait 20 or 25 years to give the Nobel Prize because it kind of takes that much time for the importance of the discovery to become apparent. You know, like if there was one a few years ago for something called the green fluorescent protein, and some guy just realized that there's a kind of jellyfish, I think, that produces this green fluorescent protein that glows green if you shine light on it. And he isolated the protein and the sequence of DNA that codes for that protein that makes green fluorescent protein. And everyone's like, oh, that's pretty cool and whatever. But it turned out to be ultra valuable because people then took that DNA sequence and could splice it into DNA codes along with some other DNA code. And it enabled them to look at the cell, and if it glowed green, they knew that they were successful in splicing it in. So basically genetic engineering after that, for like research purposes, not for, growing crops or things like that, they had a way of telling when it was successful and when it wasn't, because if the green fluorescent protein also went, they knew they would have both gone in successfully. So it basically it gave a tool to people that were doing genetic engineering to be able to see what had happened. And so the person who first isolated it and found the DNA sequence never probably envisioned that outcome, but it ended up winning a Nobel Prize because of the work it enabled afterwards, right? So that you see that sort of thing, that they make a discovery that maybe on the surface doesn't seem that impactful, but somebody else takes that and or many other people take it, and really it sort of opens or gets over a big hurdle in an industry that way. So it's pretty cool, I think.
Or you die before you get awarded the prize.
I don't think I've done anything. That's good. Yeah. And actually, it's true. You can't get the Nobel Prize if you're dead. Except there's one way you can get a Nobel Prize if you're dead. Because they announced the prizes this week, but they don't actually confer the prizes until there's a ceremony in Sweden months later. Yeah, so you can die in between and you still get the prize, even though you were dead before the prize was conferred. But you have to be alive when they're announced. So that was a problem with Watson and Crick.
I did Randy's Women in Science course in the summer, and she was wrong. I forget her name, right off the top of my head.
Rosalind Franklin.
There you go.
So she did the X-ray crystallography to figure it out. But she died before the prize was given out.
From cervical cancer.
Was it cervical cancer?
Pretty sure it was cervical cancer.
Yeah.
And then one of the other peer was helping to take care of her before she died.
Oh, really?
She never found out that they had stolen it.
It's nasty.
It's a real.
Yeah.
That's probably one of my favorite courses I've ever taken. It was so good.
Yeah.
But it's just so much rage.
Yeah. Such a history of that, and going back to Marie Curie, and that's
Yeah, we covered her too.
that's a while back. It's 120 years, and she had such a struggle getting a professorship, and she initially was, I think, only allowed to work in the university because she was married.
Under a man.
Yeah, and it was her husband.
At that time, you were to get your husband's degree.
Yeah, yeah. And then I think after she won the Nobel Prize, I think they, probably begrudgingly for some of them, kept her on. Yeah. But things have improved. Not to say they're perfect, but Marie Curie's daughter, I think she has 2 Nobel Prizes.
It's the only mother and daughter duo in history to get both Nobels. Yeah.
Yeah.
And she was there for her daughter's presentation too.
Oh, cool.
Yeah.
Yeah. And do you know how her husband died?
I forget, but she died from exposure to radiation.
From radiation, a lifetime.
No, he died.
He got run over by a horse and carriage.
Yeah. Yeah.
Yeah.
What a way. So she just slowly decayed over 80-some years and carried, radioactive material in her pockets. And her dress had pockets at the time.
Oh, that's helpful. Helpful. And I think actually her lab
Yeah. Oh, yeah.
her lab got considered a toxic waste site because there was so much radioactive stuff everywhere in her lab, and they didn't know what to do with it.
Yeah.
Yeah.
Do you know the story of why Nobel Prizes were made in the first place?
Yeah.
Because Nobel, he invented dynamite and it ended up being used for all these horrible uses, and then he got super sick and everyone thought that he died, and they posted all the obituaries in the newspapers describing how awful and terrible of a person he was and how terrible his invention was for the world and how much damage it did to. He was alive. He was in the hospital, and because he had suffered a heart attack when he like, and that's why he was hospitalized. And then he read all the obituaries describing how wretched of a person he was. Then he had another heart attack and stayed in the hospital for like another 2 or 3 months. And then he dedicated all of his. Yeah, he dedicated his entire life fortune to advancing world peace and to celebrating the sciences and good things. Because he wanted to redefine his legacy. Did I say that right?
Yeah. Yeah. You said it really well. So that's my understanding. Yeah. And it's crazy how like there's certain individuals that like stand out for like either the good they did or the bad they did. There's another chemist, and he discovered what was it? He discovered like 3 things that were all like super popular, but all really negative. Like DDT might have been one of them.
Is this the guy who invented leaded gasoline as well?
I think so, maybe. And there was a third, maybe, like there was like all these things, and like every one of them like turned out to be like widely adopted, but terrible for the either environment or health, you know? It might have been like the other one might have been like a nerve agent or something, like a, you know, like a poison gas used in the war or something like that. Like maybe Agent Orange too.
The thing, like, you can develop things, it's what other people do with them.
Yeah.
And that's what energy.
Yeah. Exactly. Yeah. Like
Fertilizer can make bombs when people were making fertilizer? Probably not.
yeah. A lot of people did that.
Yes.
Yeah. I just figure I should probably